Hello and welcome also from my side. The topic of my presentation today is the reliability challenges of power electronic modules. And I have structured, okay, this works very nice. I structured my talk today in the following form. I will start with a small introduction of the ERE as our working group. ERE stands for Environmental and Reliability Engineering. This is the department with which I was a part from, and our working group is the System Reliability Assessment Working Group from the Fraunhofer ISATM. Then I will point out some typical failure modes and failure data analysis from two examples of application fields. An example for emission profile, and then I will discuss a little bit the question sustainability versus reliability for the background of power electronic, and then I end with a small conclusion. So yes, our mission of the Department Environmental and Reliability Engineering is to support the development of sustainable and reliable microelectronic systems using with a systematic assessment. And we deal with topics of aging phenomena of micro and nano scales and here in detail the assessment of the warpage issues of substrate level in the production field. What is a very important topic of us is the design for reliability on module and package level, and we tested and analyze the behavior, the reliability behavior of such electronics with combined load lifetime tests. Yes, and some different topics is here the accelerated test planning, the system reliability and the emission profile, and last but not least, the condition monitoring of electronic systems. For this, we have a lot of test equipment, temperature, humidity tests, mechanical stress tests, our power lab with different test facilities according to the RQG 324 automotive guideline from the ECPE. And on the analytic side, we have a lot of non-destructive, destructive, and electronic test facilities for optical inspections and thermography, the destructive analysis for microstructure analysis and element analysis. Sorry for the break. And yes, comes to the topic, the reliability challenge and the power electronics module. The meaning of module can vary, or variation of the dependent on the area of application. So system developers, if they speak from a module, they mean such a model which what you see here. It's an semicron model and skip module with a weight of 3.1 kilogram. If you discuss with partners or with colleagues they come from the wind turbine, from the operation side, they speak or they mean when they say the word module, something like this. This is the Delta module from General Electric with a weight of 100 kilos. It's a little bit difficult to, here you have an more than in system, but this have same meaning if you say for the guys it's a module. Here you have the DC link capacitors integrated. You have PCB from the driver electronics. All are located here inside, and this is when you have to do an failure analysis. This more difficult or more here have you more to do. But for both, reliability means you have an stable lifetime or you have an reliability system, not such as you see here in this picture. This system has a very big problem. The typical power electronics module failure modes in the package. You have the cracks on the die attach, you have delamination on the substrate level. Here, you see delamination of the DCB. You have cracks in the bond interfaces or heel cracks of the bond. You have electrochemical dehydration on the surface of your die. All this can reduce the lifetime. All this decrease the reliability of your module, of your package. But more common failure mechanism of the system application. You have fatigue fractures. You have the growth of intermetallic phase. You have electromigration, corrosion. If you have humidity in the immersion profile, whisker formation, dendrites from mechanical vibration loads. You have electrostatic discharges, thermal aging, or an oxidation of polymers and new laminations. And you have more and more and more failure mechanisms. All this you have you need to have in mind when you say, I want to increase the reliability of the power electronic application and the power electronic system. Here I want to show you some failure data analysis from wind turbines and photovoltaic. Here you can see for the wind turbines a very high number of the main failure components are the phase module components with the IGBT modules, the driver boards, the DC link capacitors, and the bus bars, and the inverter control. On the photovoltaic side, here, for example, you see the analysis of a string inverter and 2,000, more than 2,000 failures out of a database of 8,000 are categorized here. And here, the main failure components, also the semiconductors and electromechanical switches. In a string inverter, you have a lot of PCB integration, so the PCB errors can lead to power semiconductor defects. In most cases, it's not possible to differentiate between driver PCB and semiconductor at cause on the system side. The downtime for the wind turbines. Here we can see that we have seasonal failure patterns and very high cluster, what you see here for the seasonal time from June to September in India with higher relative humidity and higher temperature. Here we can see a significant effect which comes from the humidity, and the analysis shows that the phase module failure rate doubles with each of 5 grams per cubic meter higher mean ambient absolute humidity. You see an similar behavior for an Scandinavian wind turbine fleet. For the photovoltaic system downtimes, here in the data set A for a string inverter 2, the failure occurrence considered all failure categories match with the higher irradiation and ambient temperature and also with the higher absolute humidity. No match we will find with the season of higher power generation in the spring and the autumn, but for the season with higher absolute humidity, you see more inverter failures. Here a look more in detail. What you see here is the failure time per day or in a day. Mostly the highest number, it's 34%, occur with the maximum power point at the noon time, but 30% of the failures occur during the inverter startup. The inverter startup characteristic, the procedure is here point out. It begins with a relay test, insulation resistance measurement, and mostly the residual current sensor test. And here, mostly in the morning, in the startup phase, you have what you see here for a sample of days, the highest relative humidity, which comes from the dew formation from the night of the information of the humidity, and a lot of failures point out at the within a um, low um, power peak on a low power peak. Here you see um, this bar stands for a power peak of 10% from PAC to P norm. So the humidity is a very important or a very hard driver for the decreasing of reliability in the inverter system. This brings me to the topic, the emission profile. You see that the humidity is on the one side. Thermal load is a very dominant driver for the failure mechanism, and also the humidity. The emission profiles, what you need for the best or for an realistic testing is very important, and it's not only three facts. It's not you cannot say, okay, I need an stable system or an stable electronic in the temperature range of -40 to 150 or 175 degrees C. That's a number which comes most friendly from the automotive guys. The mission profile is a combination of the general requirements which comes from the outside load, the installation conditions, the use cases and operation scenarios of the. For this, you need a data acquisition, data processing, and then you can build up a load collective, uh, which is necessary for reliability estimation. This is here you get your climate data, or you need the climate data, and for this you make an table with the yes, important, or for the times which you have the load in for your system. This is dependent from the mounting place and from the operation behavior. Oops. And this in a combination with the climate data, you get some such an Fourier diagram, which build up the load collectives. And this you need for the yes, for realistic testing behavior. But it's very important to get in mind how much reliability is necessary for a sustainability system. The sustainable key aspects are you want to have a low impact of the environment. This is one of the driving forces for the power electronic system. You want in your production, you want an environmental friendly production, you want a low CO2 footprint, low material usage, and mostly environment-friendly materials. And at the end, the your system have to be recycling or have to be good to recycle. And on the other side, you want a long operation time, which means you need a high reliability and a high robustness. But how it's very important to bring this in an yes, you bring this together. Increasing the operating time means you increase your reliability, but you want to have compact power electronics module. You have to increase robustness. You need a high effort at the materials. Mostly comes this together with the high costs. You have a high number of different failure mechanisms in harsh environmental conditions. Wind turbines offshore, there is a high harsh environmental, and you have a high humidity load, temperature and mechanical loads, and mostly the humidity loads. If you make you want to have compactor and smaller modules, so your diffusion paths for humidity decrease, and so your on the other one side you get um, you need not so much material, but on the other side, it's a problem with the robustness from the humidity side, and very important for these question or for these challenges and the reliability is to have in mind power electronics should be sustainable, but how much reliability is necessary to be truly sustainable. And this brings me to the end of my talk, um, my small talk, and I hope have this conclusion. Um, Important is to in these or the one of the biggest challenges in the reliability testing is the development of the right test procedures to reduce the or to reproduce the dominant error patterns from the various of application areas. You need application specific mission profiles in details, and for renewability energy supplies, wind turbines and photovoltaic systems, there are different. This is important to have in mind. Also for automotive, all these application works in the environment, but the mission profiles are different, and you have multiple error images from the various field application, and and here is a big um, lag from the test to the field um, error images, and this is a very big challenge too, and the reliability to have an to increase the reliability, you have in mind the system level. All systems work under combined loads: temperature, humidity, vibration, and much more. And the dominant failure mechanism can change in depending of the area of application. And the biggest challenge is the answering of the question, how much effort is required to achieve a high level of reliability in order to realize sustainable systems? Here we have to have in mind high effort in the development phase at the materials, reduce the sustainable, so also sustainabilities reach the high costs and high CO2 footprint in the production phase. Yes, this brings me to the end, and I hope I can bring this question in your mind um, for the discussion. What are the challenges in the reliability, and what brings us to an sustainable energy and sustainable industry? Many thanks for your attention, and I'm open for questions from your side.